Hello, this is John Wallace, Senior Editor at Laser Focus World, and welcome to today's webcast brought to you by Laser Focus World Online. Today's event, Laser Measurement, will be presented by Cary, Director of Marketing at Ophir Sphericon, and John McCauley, Midwest Regional Sales Manager, also at Ophir Sphericon. Following the talk, we'll have a short question and answer session. You can ask questions at any time during the presentation via the web using your Ask a Question box by clicking in the open area and clicking the Ask Question button to submit. And we encourage questions. It really makes things more interesting at the end of the web talk. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. It is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce today's first speaker, Cary.
Hello, this is Cary. Good morning, afternoon, or evening, depending on where it is you're listening from. Today I would like to talk to you a little bit about laser beam profiling and specific to applications, matching your laser beam profiling to your application. Necessarily, this is going to be a somewhat cursory view of those things, and I wanted to mention that we have a lot more detailed information in some of our tutorials available on the Ophir website, which we'll give you later on. So let me start off by telling you what we're going to talk about. First of all, basically what I want to talk about is building an aligned optical system and how one goes about that using laser beam profiling technologies. Subsets of that are focusing and collimation of lasers. Then we're going to talk a little bit about high power beam quality measurements. John will talk about those. And then I'd like to finish up by talking about proper attenuation techniques and some of the pitfalls that can occur if you don't do attenuation correctly. So let me start with building an aligned optical system. What are some applications that would be examples of an aligned optical system? Well, certainly, first of all, say a laser printer. In this case, where you've got a laser spot that needs to be aligned to the platen or the place where the paper is being written on, and that spot needs to be of a particular size. Laser marking machines, pretty much exactly the same application, just generally a higher power laser mark is needed depending upon the material the marking machine is designed to mark, whether it's plastic or diamonds or pieces of metal. But in any case, it's going to do the same thing. You've got a laser spot, and you need to put it at a certain size in a certain place. Rangefinders, sights, LiDAR. In these cases, we're trying to align a laser beam to a target and keep it aligned with that target and with the sighting device, whatever it is, whether it's a rifle or a missile or some application that might be less lethal, like LiDAR, which is looking at a standoff type of chemical analysis and things like that. Another example would be laser projection systems, and here you're needing to superimpose multiple spots on the same place so that laser projection can give you the colors that you need to show the pictures. So those are examples of what I mean by an aligned optical system. There are certainly many more, and we'll talk about some more as we get into some of these other applications. So what are we trying to do? As I said before, we're placing a beam of a certain size at a certain place in space. And the simplest way to do that is to put the profiler where that spot needs to be made and make both of the measurements, a beam size measurement, which you can see down below in that display showing two beams there, and a position being shown over there in the pointing window. So basically, with a profiler, you can make the two measurements that you need to make for this alignment process: beam size and beam position. Profilers come in various types, and both of these, and all of these techniques can be done with either a CCD array, or what we call a camera, or with something like a scanning slit profiler. Both of them are capable of doing both the beam size and the beam pointing measurement. Now, which one you choose has to do, to a certain extent, with what exactly you're trying to do, how big a beam you're trying to look at, how much fussing you want to do with your instrument versus your aligned optical system. Scanning slit profilers have an advantage in that they can measure a much smaller beam, and they can measure it at focus quite often without any attenuation. CCD arrays can give you more information about the beam size or beam shape. It can measure beam sizes, but not quite as small as scanning slit. So a CCD is going to be limited to something around 10 times the pixel size of that camera. So with modern camera systems, arrays getting down in the 4 to 4.5 to 6 micron area, we're talking about somewhere around 40 to 60 micron beam spot sizes being sort of the bottom limit of what you can measure with a CCD. Scanning slit profilers can actually get down to under 10 microns. So it gives you those two opportunities. The other advantage that you, as I said, with scanning slit is you don't have to usually put any attenuation in the beam, and this makes it much easier to look at, say, a focused beam, because it's very difficult to get a focusing beam through the attenuation and onto the surface of the array accurately enough so that you're actually measuring at focus. And we'll talk a little bit about how you do that if you need to use a CCD. So for pointing accuracy, in general, the application is you put the profiler where the beam is to be aligned and align the beam to that profiler, to some point on the profiler, the center of it, or some predetermined position. Now, one of the things to realize with pointing accuracy is you've got several aspects of the pointing that are going to impact how accurate you can measure it. First of all, you have the accuracy of the profiler itself. In the case of a camera or a scanning slit profiler, this accuracy is going to be on the order of sub-micron accuracy within that instrument. But you have to also remember that pointing accuracy is a function of how well have you got that profiler fixed, how well do you have your laser source fixed, and so fixturing will also be very important to maintain accuracy in a pointing type of measurement. On top of that, you have some external influences that can influence the pointing accuracy. Air currents, vibration, localized heating, all can cause a beam to move around or to be defocused. Air currents can change the refractive index slightly, and when you're talking about measurements that are down in the area of a micron or less, it doesn't take much to push that off a little bit. So remember, when you're setting up a system to be aligned, it's very important to control these issues. You need a good vibration control table. You need good fixturing for both the profiler and your laser source. There's also an issue of linear and angular alignment, which is fairly complicated, and I really don't want to go into it in this talk because it's covered very nicely in a pointing and stability tutorial that we did that's available on the website. So I would refer you to that. It's called Laser Pointing and Stability Measurements. And it talks about the difference between linear and angular. But linear would be the up and down motions of the laser, and angular would be how it is pointing. And in general, what you're trying to do is align the pointing of the laser and trying to get rid of any of the additional motion that would be the linear motion. So this would be your vibration or anything that has to do with the fixture not being as stable as it should be. So I'm going to skip over this next slide and go to where we talk about focusing and collimation. Now, focusing and collimation both are part of this alignment. This is where you're making the beam have the right spot size or the right focus or the right depth of field or depth of operation that you want within your aligned optical system. Focusing is a very simple application for low power lasers, such as is done for optical telecommunications or scan systems, where we're talking about lasers on the order of a couple of watts or less, because you can just put the profiler where you want to make the focus and make the measurement. It gets a lot more complicated when you get to higher powers, such as ophthalmic surgeries or therapeutics, laser marking systems, precision welding. In those cases, you may have to do some other things in order to find the focus and be able to measure it. So first of all, as I said, it's very simple in a low power situation. A typical application, for instance, would be a free space optical coupling of fiber. So you're putting a lens. They're called GRIN lenses or gradient index lenses. They're put on the end of fiber, and they form some kind of a waist or even a collimated beam. And you just simply measure them by putting the profiler right where you want that waist, measuring the waist. Now, if you have a scanning slit profiler, you can actually know exactly where that measurement plane is to within several microns. And so you can find the waist very precisely. And because you're in a low power system, you're measuring it directly. You don't have any problems with having to figure out a way to attenuate that beam. Now, when we get to higher powers, we may have to do some additional things. There's a couple of approaches to that. Now, one of the things about a focused beam is that high power can be defined many different ways, but in general, what we're talking about with a focus beam is power density. In other words, a 1 watt beam focused to several hundred microns is no problem to measure directly. A 1 watt beam focused down to 10 microns may in fact have high enough power density to actually damage a profiler. So what do you do about that? Well, there's a couple of approaches. One of them is to add a lens where you have a known working distance on this lens, a fairly short distance, and you actually image the waist focus point and blow it up so that it's larger when it gets to the profiler. This lowers the power density and makes it possible to measure that. So we can do that with a scanning slit profiler. So for instance, say we have a 10 micron beam that we need to measure. It's at 2 watts. We find that, whoa, that's high enough that it's going to damage this profiler. So what we can do is actually image this with a 10x lens that blows this up to 200 microns when we measure it, and so we don't have the power density that's going to damage anything. When we're trying to do a focus spot analysis using a camera, we have some other issues. Mostly, we have to use attenuation to get to the camera, because cameras are so sensitive that pretty much any laser is going to saturate the array or possibly even damage the array. So we have to put some kind of attenuation in. If you've got attenuation and you're trying to measure a focus spot, think about that. You've got to go through this attenuator with the focus, and you can't really do that. So again, the way to look at a focus spot with a camera is to image it. So again, in this case, we have a lens here. Then we have the attenuation. In this case, we start with some wedges and then go through to gray glass filters and get the power down to the level where the camera can measure it. So measuring focus spots with cameras tends to require some kind of lens and system, whereas in most cases, scanning slip profiler can measure the focus directly. If it can't, then we can put some kind of optic here. This could be a microscope objective if we need to blow it up larger than 10x. It can be an A-sphere lens for 10x or 20x. In either case, we're able to then measure the beam at focus. Now, collimation is sort of the opposite of focus. So what we're trying to do with collimation is to extend the laser beam into a long-range type of usefulness, as you will, thinking of the beam as maintaining a size, a useful size for a long distance. Now that can be a relatively short long distance, like say with the scanning, the scanners that work at point-of-sale scanners, like in the grocery store. There you want that beam to work over a range of a meter or so, so you don't have to hold the barcode exactly in one spot. And you know, it will read that barcode if the thing is held anywhere within a certain range of a couple of feet or a meter or so. Now, LiDAR, for instance, that we're talking about trying to do something over kilometers. So again, we're trying to make a beam that has a useful diameter for a very long range. The same is true of laser rangefinders, guide stars for telescopy. Is that how you say that word? Free space optical communications, where we're using a laser beam through free space, and putting a signal on top of that and using it as a communications link. All of those require a very long range beam that stays relatively the same size. This is what collimation is. So basically anything that needs a long range uniform beam. Well, it turns out there's two kinds of collimation. There's what we can call a maximum distance to the waist collimation, and then there's a collimation that we can define as minimum divergence, and they actually are different. If we look at the maximum to waist distance to waist, the easiest way to do that is to place a profiler at the working distance. Now, if that working distance is several kilometers away, then we have to do some calculations instead, and basically calculate the divergence measurement that will give us the distance to the waist that we're looking for. Now, this is covered in great detail in Donald O'Shea's classic work, The Elements of Modern Optical Design, written in 1985. I believe it's been updated since then. But the copy I have, pages 241 to 245, discuss how do you make this calculation of the maximum waist distance. If we look at the formula here for calculating the divergence is the opposite of collimation. Again, divergence is how much is the beam spreading. If we look at this formula here that you see, theta is the divergence, df is this beam measurement at the focal length of the lens, and f is the focal length of the lens. So if we take a lens of a known focal length place the profiler at the geometric focus of that lens, and then make adjustments out here to your collimating elements to minimize the beam size at the profiler. That will give us the minimum divergence. Now, as you can see, because lasers don't go to zero, you can't get a zero divergence. There's always going to be some divergence in the beam. And this is why this measurement actually comes out slightly different than if we just try to maximize the waist to infinity. So there's, again, you have to look at what is it I'm trying to do. In this case, if I'm trying to build a system that gives me a collimated beam over several meters, this is probably one of the best ways to do it. If I need to calculate the divergence value that I need in order to get the waist to the maximum, because I don't want to go out and try to get a profiler and set it up 10 miles away from my laser, then you would use this method as well to make those measurements. And the one thing to recognize also is that this lens geometric focus is going to be different for whatever wavelength of light that you're trying to measure. Lenses are generally specified at a particular wavelength. So a 200 millimeter lens is exactly 200 millimeters focal length at 585.2 nanometers. Why they chose that, I have no idea. So there's a correction factor that's involved if you're, for instance, looking at 532 or 632 or infrared at 10.6 or 1.06 microns. So you will need to make a correction, and there's tables of those corrections because you want to put this at the exact geometric focus in order to get the accurate measurement of divergence. So, with that, I'm going to turn this over to John and let him talk to you a little bit about making measurements of high power systems. So, John?
All right. Thanks, Alan. Appreciate that. First, I also want to say hello to everybody and thank Laser Focus World for hosting us today. I do appreciate that, for giving us the forum to talk about different laser measurement techniques. Also want to thank Laser Mechanisms for providing us with a couple of different pictures throughout the presentation. I didn't note it in the slides here, but they provided us with a couple of the different pictures here, and I certainly want to thank them and give them credit for doing that. So I'm going to be talking about high-power beam quality measurements. I'm the Midwest Regional Sales Manager, and so most of my applications of the laser measurement equipment that I sell are with industrial lasers, or lasers that put out hundreds of watts or even up to several kilowatts of average power. So there are some different schools of thought and some different techniques for how to take those types of measurements that I wanted to speak about. So what measurements should be taken? You've got a laser. You want to ensure that you've got beam stability over time, that kind of thing. So what measurements do you take on a laser in order to ensure that you have that stable laser? First one is output power and energy, and we're talking primarily about beam profiling in this presentation, but do want to make note that it is important to measure how much output your laser is taking or putting out. So taking an average power, single shot, or multiple pulse energy measurements is certainly important. Second, you want to take what's called the spatial profile or the beam profile. You want to know what the laser is doing across the beam, how the energy is distributed across the beam, what kind of mode you have, because that certainly is going to be important when you're talking about a laser that's interacting with material. You also want to know what your laser is doing not only at the focus spot, but around the focus spot. So caustic measurements, what the focusability of the beam is, that certainly is important when it comes to applying that to your process, what it's doing around the beam waist. And finally, if you do have a pulse laser, it's important to know the temporal profile, or what the energy is doing with respect to time, what the pulse shape is. So why should measurements be taken? I get this question asked a lot. You know, John, you're giving me these data points. You're giving me, you know, how much power is being output. You give me pretty pictures on a computer screen. So what do I do with this information? And in general, how I would answer that question is to ensure that you have a stable, a reliable, a consistent, and a repeatable laser process. You've got this laser process, and in order to prove that you have a quality laser process, specifically that you have a consistent process over time, the process has to be measured. You have to measure what your focus spot is. You have to measure what your energy is doing, you know, across the beam, and you have to measure how much power or energy your laser is outputting. A laser, fact of the matter is, a laser system is made of matter. It's made of stuff, and it will degrade over time. So because of that fact, you have to measure what your laser is doing over time just to make sure that you do have that quality laser process over time. And unfortunately, laser system components sometimes catastrophically fail. And when that happens, how do you ensure that your laser process is as good after the maintenance as it was before the maintenance? And you ensure this by taking laser measurements before and after your maintenance, just to make sure that your laser process remains the same. So when should the measurements be taken? Now, I realize we're talking with a lot of different laser users today, so I'm keeping it kind of general and trying to include just about everything that I can think of. But when should measurements be taken? Laser system development and the manufacturing. So if you are a laser manufacturer, you obviously need to be taking measurements on your beam just so you know that you are supplying your customers with the highest quality laser that you possibly can. During application development, when you are developing a process for a laser, if you're an integrator or a laser manufacturer or even an end user, if you're developing an application of that laser, you need to know what the measurements of that laser is, so that when that process has been approved and you need to transfer it over to a manufacturing process, you need to know that when you make that transfer to the other laser system, that your beam looks exactly the same or as close as possible when you make that transfer. Measurements should be taken during a system runoff or a factory acceptance test. You need to be able to ensure that the laser is performing the same as during the application development. I mean, it makes sense that you developed a process. You want to make sure that when you have that process transferred over to the production laser, your laser is behaving the same. Anytime that you've got a system delivery, so for instance, from the integrator to the end user, or if you need to move that system, you need to make sure that the laser is behaving the same before the move and after the move, so that you can ensure that that process is stable. During process validation, if you're moving or copying a process from one system to another, you need to make sure that those two different systems are performing exactly the same, so that your process will be the same. During batch validation, you can take measurements, or you should take measurements to prove to your customer that the laser remained consistent during that process of, for instance, a batch of parts, or you know, a periodic check. You know, if it's an ongoing process, you need to measure your laser, you know, once a day or once a shift even, to make sure that your laser is performing consistently over time. And then obviously with laser maintenance, when you're doing any component changes such as optics or lamps or fibers, things like that, you need to take measurements just to make sure that before and after shots of that laser remain the same. Sometimes you'll you'll have a laser that's not performing properly. You need to measure your laser in order to troubleshoot what's going on with that laser. And any time that you've got a situation where you need to modify the laser parameters, change pulse width or change power output, that kind of thing, you need to validate, or you need to use the equipment to make sure that that those changes to the laser parameters had a good effect. So what technologies are available for laser measurement? Now, again, we're talking primarily about beam profiling, but again, like I stated, power and energy measurement certainly is a bit of data that you need to measure. So in order to do that, we've got thermal sensors, which measure the laser power, the average power, or the power of a CW laser, as well as single pulse energy. Thermal sensors will read those as well. And we also recommend pyroelectric sensors for measuring repetitive pulse lasers. So those are the technologies for doing that. Beam profiling, Allen kind of talked about this, but what we offer, and what a lot of companies offer, is camera-based profiling. So by use of an attenuation device, the laser is sampled down to a lower power that can be measured. And these systems are typically good for measuring beam size, beam shape, spatial energy distribution, beam wandering, etc., etc. And then it's also used for measuring the focus spot of a laser, like the system that's pictured here is typically used for measuring the focus spot of lasers. A rotating pinhole is another technique of measuring specifically around the spot, or the caustic of the beam. And with this device, a small pinhole is presented to the beam, allowing for a small portion of the beam to be detected at a time. Data points are then used to compile the image of the beam. So it's you see to the image off to the right here. You see the slices of the laser beam and how that energy is distributed around the focus spot. So it's used for measuring the beam profile, used for measuring the caustic or the beam waste, and also providing an m² value, or the focusability of that laser beam. This particular device here it uses a spinning wand. So this device is used for the beam profile of raw beams of CO2 lasers. And how this device works is it uses a spinning wand or a mirror, and it samples a small percentage of a collimated beam and sends it to an imaging device, and then uses that image to feed into beam analysis software. And the uses of this device are for measuring spatial intensity across the beam, your beam size, and your beam shape as well. Here's a picture of, showed earlier, but it's more or less an all-in-one system. So we've got, at the top here, we've got the delivery head, or the processing head. It's attached to a robot here. And then the focus spot is somewhere below that head. In the middle there, we see the focus spot analyzer, and this device is made by Primus. It's a focus monitor. And then below that, you've got a device that's measuring laser power. So you've got the beam profile, and as well as the power measurement, all in the same system. This device, this collection of devices here, kind of gives the same information, a little bit different way of collecting the information. To the top right there, you see a camera that's attached to the attenuation device. That's going to give you your spatial profile, your beam size. Underneath that, you see a thermopile sensor. This is going to be collecting the majority of the light and giving you your output power, or in this case, it's a single pulse laser, so it's going to be giving you your energy per pulse for the single pulse. And then to the lower left, we see what's called a fast photodiode. And what that's going to do is interface with a PC-based oscilloscope, and that's going to give you your temporal pulse shape. So you've got with this system, with this collection of devices, it's going to give you just about everything that you need to know about your beam. Here is another all-in-one system that's made by Ophir and Spiricon. This device is called a Beam Cube, and it's a beam analyzer that, again, it gives you your your output power. It's going to give you your focus spot size and also tell you how the beam energy is distributed across the beam, because it is a camera-based beam profiler. And also, the device has the ability to measure your temporal pulse shape as well. So this device here is also another good all-in-one system as well. That's really all that I've got to present, so I'm going to send it back over to Allen to wrap it up.
Okay, so I said at the beginning that one of the things I wanted to talk about was proper attenuation design, and we've mentioned attenuation along the line here, talking about what you needed to do with cameras and occasionally with scanning slits, certainly with high power systems. What is attenuation? It's a method of knocking the power of the laser down to a level that can be measured without damage or saturation in the profiler. And so the problem is you have to do this correctly, or you get the wrong answers, and that's the bottom line. So what are the applications for attenuation? Well, pretty much any laser measurement application may require some kind of attenuation. This is particularly true if you're using CCDs or arrays. As I said before, CCD or array type profilers are first of all very, very sensitive. Second of all, they take the entire beam focused onto their or incident on the array, which means that, unlike a scanning slit, which is only taking a very small portion of the beam at any one time and putting it on the sensor, with a CCD you're putting the full beam incident on the array. So it's at very low power. We're talking well below the power of that lasers come in. You're going to saturate that CCD array. And in that case, you can even damage them, depending on the wavelength and certainly depending on the power levels. As an example, a 1 milliwatt laser, so your typical Heaney or laser pointer, is going to require about 3 orders of magnitude of attenuation to be able to be profiled by a CCD without saturation. So what that's saying is that we need to put in somewhere on the order of a microwatt is about where the CCD is going to be happy. So that means obviously any laser that you want to measure is going to require some kind of attenuation. Scanning slits, on the other hand, can generally take powers up into the watts, even up to there are systems that can handle up to a kilowatt. But when you get the beam sizes very, very small, as I mentioned before, you get very high power densities, and then you can damage the scanning slit. And so you need some kind of attenuation, again, for that. So if we want to look at the process of attenuation, we have several types of attenuators that are available. The most common type that you're probably familiar with are the gray glass or what we call absorptive filters. These can be made of glass. They can be made of rattan material, which is a sort of a plastic material, or they can be made of something like Inconel, which is an absorptive filter for UV. A glass obviously is going to attenuate UV completely, since it's pretty much opaque to the UV light. So this, as you can see on the front of that camera system there, that dark circle is typical gray glass filter. That's probably what we would standardly see at 2.8 neutral density, almost 3x type of attenuation. We also have what we call reflective attenuators. Those can consist of laser mirrors, which are the mirrors that they put into a laser system, and they would be a leaky, think of them as a leaky mirror. In other words, they reflect about 99.5% of the beam, and about 0.5% of the beam will leak through. And so that kind of attenuator can be used to reduce the power about the same as a 3x gray glass filter. We also have things like front surfaces and prisms. These can be either AR coated, that's anti-reflective coated, in which case they're going to reflect a very, very small portion of the beam, less than 1%. Or if they're non-coated, typical quartz prism or quartz wedge will reflect about 4% of the beam. So it lets 96% go through, 4% is reflected. And in those cases, you generally take the reflected portion and use that to measure. So what's the problem? Well, there's a problem called thermal lensing. And it's quite possible to stack up an enormous number of gray glass filters and cut the power down by many, many orders of magnitude. But what happens there is if we start with a high power going into an absorptive filter, the material of that filter will heat up. Now, if it's a glass filter, it will heat up and you won't see anything. If it's a rattan filter, it may heat up and burn a hole in it. But if it's a glass filter, it still heats up, and that heating changes the refractive index of the material, the BK7 glass or the quartz that it's made of, and it will form a lens, and that lens will distort the beam and give you erroneous results. This tends to happen at power levels that are, as a rule of thumb, we like to say about 100 milliwatts per millimeter diameter. So it's a quick back-of-the-envelope way of thinking about it. Okay, if I've got a 100 milliwatt beam and I'm going to focus it below a millimeter, then I'm going to have a thermal lensing problem. If I've got a 1 milliwatt beam, you probably aren't going to see that problem because you'd have to make it awful small before it would cause the problem. But as lasers have become more powerful, we're seeing this more and more often because people are trying to measure 500 milliwatt lasers, 100 milliwatt lasers. And the problem is this happens very fast. Back in the old days, they used to call it thermal blooming because lasers weren't very powerful, and so you'd see it happening. You'd be watching your laser profile, and all of a sudden it would start to get bigger or smaller, or it would change. And that was as the material was heating up. Well, now, with these higher power lasers, it happens very, very quickly. And as an experiment to show this, we did an experiment here by setting up a 500 milliwatt laser and measuring it in 3 different ways to show what happens and how thermal lensing can occur. So the first method, we used a CCD beam profiler, and we did all the attenuation using the absorptive style of filters, gray glass filters and a variable wedge filter, both made of a gray glass, or kind of, you can think of it as sort of sunglasses type of attenuation. We measured the beam at a point 30 centimeters from the exit aperture of this laser and took the results. The second method, we did exactly the same thing, except we set the first stage of the attenuation to be reflective. So this would take the first step and knock the power down before we put it into an absorptive style of attenuator. And then as a control, we took a scanning slit profiler, which didn't require any attenuation at this power level, and measured directly at the 30 centimeter point from the aperture as a control. So here's what we saw. Using that first technique, we noticed we got a nice measurement of about a 0.5 millimeter. 512 in one axis and 412 in the other axis, and it looked like a pretty stable, pretty reasonable measurement. But if we looked at that measurement using time charts, we could see what was happening over a very rapid period of time. You'll see those spikes, and what that was done is when we covered up the beam and then let it back onto the profiler, we immediately saw this spike, which then settled right back down to the 500 micron size again. So we said, okay, you see that happens very, very quickly. These were samples taken at the frame rate of the camera, which is about, which I think in this case was somewhere in the order of 30 hertz. So as you can see, in very short order, it would come down. So you really wouldn't see that unless you were looking at it with some kind of time charting capability. So we replaced that first stage of attenuation with the reflective attenuation and made the same measurement. And now we see that, in fact, that spike is close to what the real beam size is, around 800 to 900 microns. So much closer to a millimeter than half a millimeter. And when we took the control measurement with the scanning slit, we saw the same thing. Here we have a scanning slit, no attenuation, no external influences on the beam, and in fact the correct measurement is at 850 or 900 microns. And so as you can see, if you don't do the attenuation correctly, you can have some very erroneous results. Absorptive filters can be added up to provide a lot of attenuation. But if you fall into that trap, you are very likely to be making measurements that are not correct. And you'll see what looks to be your beam size, but it really isn't your beam size. And so it's important to always remember to start with reflective attenuation and get your beam size down below the thermal lensing threshold. And that is, as I said, 100 milliwatts per millimeter of diameter, or a power density of 1.3 kilowatts per centimeter squared, if you think in terms of power densities. That's the thermal lensing limit. And if you stay below that, or if your laser is below that, you shouldn't see thermal lensing problems. But if you are above that, and you don't use reflective attenuation, you will have problems with thermal lensing, causing error in your measurement. So anyway, that's our presentation. I want to thank you for listening to it. We'll certainly open this up to questions now, and so we'll try our best to answer those questions. I know this was a very cursory approach to this, and certainly if you have more detailed questions about your specific applications, go ahead and ask them, and we'll try our best to answer them. Thanks again.
Okay, thank you both, Alan and John. This is the Q&A portion of the webcast. So to ask a question via the web, type your question into the open area of the Ask a Question box and click the Ask Question button to submit. So I'm going to start with a nice general question, then we'll get into more specifics. Where is that? Oh, what end markets are the biggest users of laser measurement?
Oh, the end markets that we typically sell our equipment to, like I talked about in my presentation, were industrial laser end users. We certainly sell our equipment to laser manufacturers and OEMs. We have a lot of DoD customers, those, I could tell you, but I have to kill you kind of applications. And then also we have a lot of customers in academic uses of lasers where they're, doing who knows what, but those are typically our markets that we sell to. Alan, can you think of any others that I?
Well, yeah, I would say one of the areas where we have, particularly in the scanning slit marketplace, the people who are building some kind of a aligned optical system, and so there's a very, very large market, for instance, in laser printer manufacture. Most of that occurs in Asia. It's very big in Japan, and a lot of it's been moved into China and other places where they're building the scan engines for laser printers, laser scanners, any of these processes where you're trying to make a laser beam do something. Another area where we have a lot of where laser measurement is really important tends to be in the healthcare industries, particularly when those customers are following good laboratory or good manufacturing practice, and they need to measure their lasers that are doing whatever it is, whether it's building medical devices or actually the laser itself being the medical device. In either case, those customers are a large portion of the laser beam measurement world, because they are really required to measure their lasers by their FDA good manufacturing practice approvals and such.
Okay, I'm going to inject a couple of my questions, my own questions here, just to clear something up. Does Ophir Spirocon sell attenuators, or is that something that the user would have to get elsewhere?
No, we have a number of attenuation tools to go along with our measurement devices. Some of those things can also be purchased elsewhere. And certainly our parent company, Newport, has got lots and lots of optics that can be used with our equipment as well. But we do have specifically different types of attenuators that we can provide as a system.
Okay, and associated question, do you sell the lens setup that's used in the lens method for setting the divergence?
We do have a device we call the collimation fixture, which is set up specifically to do that, and it has the lens mounted and the scan head mounted at the geometric focus. Customer specifies the wavelength, and we set it up with the lens in exactly the right place and the scan head in the right place to make those measurements. Yes. But it can also be done with just a lens. You know, someone can set their own system up as well.
Okay, yeah, as long as they have good optical knowledge, they can set that up, yeah. Here's a question I think for John. Are there any emerging technologies for making measurements on high-powered lasers?
Yes, actually there are. And I probably should have talked about this a little bit in my portion of the presentation. There are a couple of technologies that are currently in development that will measure specifically multi-kilowatt lasers. Measuring multi-kilowatt lasers for obvious reasons, you know, you've got a lot of light focused down into a very relatively small area, and it does get challenging to measure these lasers. So as a result, historically, there haven't really been a lot of products that are able to do that. But I will say that we do have some technologies. I can't really go into too much detail about how it's accomplished, but there are some emerging technologies that we're going to be hopefully releasing later on this year that will measure focus spot and caustic measurements of multi-kilowatt lasers. So yeah, there are some emerging technologies on the horizon for those types of measurements.
And which approaches are used now to measure the very highest power beams?
The highest beams, the spinning pinhole technique that I talked about, that Primus makes, that really seems to be, for all intents and purposes, the leader in measuring caustic measurements of your multi-kilowatt beams. It can be accomplished with optics and attenuation systems, but typically, for obvious reasons, for distortion reasons and things of that nature, it's not really a very popular way to measure it with a camera-based system. But it is possible to do it with a camera-based system as well.
Okay, and we do have some specific questions here too about particular setups. One, I think this is aimed at John too. My focus plane has no room for a detector along the beam direction. Is there any way to angle the beam to the side to make accurate measurements of focus and beam profile? In other words, is there an approach you recommend?
Yeah, and that really is a tricky one when there's not a lot of space. For instance, at the workpiece with the workstation, a lot of times, unfortunately, beam profiling and even power measurements are kind of an afterthought. Where if it were approached at the integration level, it probably would have been a little bit easier to put a system on. But yeah, that is a tricky one. And to answer your question, putting a mirror in there and directing the beam towards a power measurement device or a beam profiler is certainly an option. But I think that whoever asked the question, they were. It sounds like they've tried and not without a lot of luck. So it is a tricky one. It's possible, but it is tricky. And I'm sorry I don't have much more of an answer for you than that.
Okay, here's a question more for Allen, I think, about another specific setup. How would you attenuate a 2 to 5 watt IR beam? I guess for the 2 to 10 micron focal spot correctly. This person used neutral density filters, which introduced thermal lensing. So what would you recommend?
Generally, what I would recommend for something in that area would be to start by using probably a pair of prisms, quartz prisms, front surfaces, or quartz wedges. It would depend. If your beam is polarized, then you want to use your front surfaces in pairs that are orthogonal to one another in order to maintain the polarity. If your beam is not polarized, then you can get away with using one of them. But you say it's about a 5 to 10 watt. If we put one reflective surface into it, say a standard non-AR coated, that would knock the power down to about 4% of that. So if say we're at, just to make the math easy, a 10 watt laser, the one front surface reflection will take that down to 4% of that, or about 400 microns. Which probably is still above the thermal lensing threshold, so you probably want to put another one in. So we put a second one in, and that would take it down to about 16, I think about 16 milliwatts, which would probably be okay. And then from there, you could probably use the absorptive filters to finish the job. So that would be one way to do it. Or actually, if you're going to use a scanning slit, you'd be well within the direct measurement level at that point. So if you just two reflective surfaces, and you could then probably measure that directly at focus with a scanning slit profiler.
Okay. As far as the measurement at focus, one question wants to know how do you know the sensor is level? And I think what that means is when you're doing a through focus measurement, how do you know your sensor is probably moving parallel with the beam? Or
well, that again is a question of fixturing, and any time you're trying to do precise measurements, you do have to pay attention to how you've set up your profiler. With a scanning slit profiler, you do have the advantage of knowing exactly where your measurement plane is, and that is where the slit is going through the beam. So people often ask, where's the detector? That doesn't matter. the detector's behind the slit, but the measurement is made at the slit. And you know that position, certainly within with a photon system, we know that position to precision of from a reference point. I think it's 0.75. I think it's 75 microns, so we know that position too. It might be 25. I'd have to look, but you know it to a certain precision, and that's usually sufficient to, for most waste measurement, finding the waste. Now, how do you make sure that you're parallel to the z-axis of the beam? Well, that again is generally a question of making sure that you're fixturing correctly, that you've got a good stage if you're trying to move through the beam caustic. Then you want to have a good stage that will that maintain the parallel nature. And then it's relatively easy to set that up and to check your parallelness by simply measuring the beam in a couple of positions. And if the beam position doesn't wander off of the center of the profile, then you know you're parallel. So if you move it from through that waste caustic and watch the position, as long as you don't move more than a few, whatever your limit is to how parallel you want it to be, you can tell that, if it's in the same place 5 millimeters in front and 5 millimeters behind the waist, then it's going to be parallel through the waist.
Mm-hmm. Okay, we have time for 3 more questions. Another fixturing question. For physically large setups, do you recommend a particular kind of fixturing to ensure stability of everything for best measurement?
I would say,
is that more up to the whoever is setting up the system, whoever owns the system and maybe knows most about the system?
Yeah, I think that to some degree that is kind of a difficult question to answer without looking at this, without knowing what specifically they're talking about. But good vibration control, good vibration tables, vibration isolation. If we're talking about a large, say a robotic laser and a sensor that's trying to measure the pointing of a robotic laser, so we're talking about a great big system, say it's something that welds the doors on cars or something like that. Again, it's going to be a function, first of all, of that laser robot. How precise is that? And that's really up to the manufacturer of that system. But presumably, they know how to make a system that's pretty stable and points the laser in the right place. So that end of the business would be probably pretty well taken care of by the manufacturer. And then it's really a question of mounting your sensor in such a way that it's isolated from vibration, so that's just really good laboratory design in terms of vibration and stability control.
Okay. You may have answered this question partially already, but what are some up-and-coming applications for laser measurement?
Well, I think one area is that's in desperate need of technology is, as John mentioned, these very high power lasers. We don't have really good ways of measuring them, and I think there's a large gap there that can be filled, and when it is, I think that will be an up and coming area. Other areas, as lasers move into more and more applications, I think those are where people will need to measure, and lasers keep moving into more applications. Basically, they're always doing the same thing. I think you're putting a laser beam in some place to do some work, and it's I'm not I'm not sure of what the next place is somebody's going to be using a laser, but I think that's I suppose this is a somewhat hand-waving answer to this question, but I don't know. Maybe John has some insight as well.
Yeah, I mean the system that we're developing right now is really the next product that we're going to be able to offer to specifically, like you said, Alan, the high power, the multi-kilowatt fiber lasers that are so prevalent seems to be in industrial uses. But unfortunately we can't really talk about specifics since it is under development still. But we hope to have something by probably the fall of this year as far as a product to offer to those users.
Okay, and the last question, is there a place to get more detail on any of these topics?
Yes, indeed. A lot of these specific applications are covered in various tutorials and application notes that are available on the Ophir website. If you go to the Ophir website, which is www.ophiropt, that's OPHIROPT.com, and click on the on profiling, there's a knowledge base area, and in there are a large number of these tutorials, things like talking about pointing stability, measuring beams at focus, measuring different kinds of beams. There's also quite a bit of information on the power meter side as well. So all of this stuff is available from our website. If you go there, when you go to download, it'll probably ask you to sign up. But if you sign up once, it won't ask you again for, I think it's 6 months. So you can get all kinds of information there if you're interested in specific applications and things that we've done.
I'd also like to add that it's in putting together a presentation like that, it's difficult to know your audience completely, and we realize that a lot of you have your own specific applications of lasers and probably a wide variety of different applications. So if you would like to contact one of us, and if you have specific questions about any of our products and how to apply them, we're more than happy to answer any questions via email. And we also, Ophir InspireCon, we also have a program in place where we can visit your facility on site, and it's no charge or obligation to you. And that usually is really the best way to get the questions that you have about our products answered, is on site, to where we can put our equipment on your laser system, and have you see it, analyze your beam, and oftentimes that generates the better questions and answers those questions on site. So we encourage each and every one of you to utilize that program that we have in place as well, because that usually is the best way to answer the questions.
Okay, and I would like to mention that even though we did not get to ask all the questions presented by the attendees today, the questions will be sent to the presenters, and they can respond to them later. Before we end, would either of you like to make any closing remarks?
Well, I'd just like to thank everybody for their attention and for their questions. It obviously sparked some interest, and again, reiterating what John said, we would be happy to talk to you about your specific problems and questions and laser setups. We have regional sales people within generally driving distance of your laboratory, and we're happy to come out and look at your laser system and see if it's possible to measure even if you don't have any space. So those are the things that's what we do. So certainly feel free to give us a call or look us up on the website and contact us in whatever way you wish.
Yeah, absolutely.
Okay.
I also want to echo what Alan said about thanking everybody for attending here, and listening to what we have to say. It really does say something about you that you're taking your time out of your day to come and listen to a presentation like this, because you're obviously interested in ensuring a quality laser process or developing quality laser systems or whatever you're doing. So it does say something about you for your attendance. Another thing that just kind of popped up, we also have got a YouTube channel. If you go to our website, you're probably going to be able to find it pretty easily, but we've got a YouTube channel. It's got a lot of videos on how to use the products as well. That might be helpful to a lot of you that are figuring out how to best apply our equipment in the field. So take advantage of that as well. But yeah, I certainly want to thank everybody that attended today.
Okay. Well, on behalf of Laser Focus World and Penwell Corporation, I'd like to thank Allen, Cary, and John McCauley of Vocare Styricon for today's presentation, Laser Measurement. This presentation will be archived within 24 hours and can be accessed from the homepage at www.laserfocusworld.com, which a couple people had asked, can I be sent a copy of this presentation? Well, you'll be able to download it. A reminder email message for the archive will be sent to registrants, complete with a link to the archive. We thank you for joining us today and look forward to future webcasts.